Hello everyone, my name is Khalid. Today we're taking a tutorial number 1 on gas mixtures, part of the Applied Thermodynamics course for third year students, mechanical engineering in Universiti Sains Malaysia. Hopefully you find this tutorial useful. You can pause the video and read the question. Here we have the mass fraction of the gases. We have to calculate the mole fraction. We have here isobaric expansion at constant pressure. We can convert from mass fraction to mole fraction using the molar mass ratio, but we don't have here the molar mass for the mixture, so we have to take another approach. So we take assumption that we have 1 kilogram of mixture. So in this case, since we have 35% is nitrogen, so the mass of nitrogen in this case will equal 0.35 kilogram. This is not absolute value, this is specific value. So the mass of helium will be 0.65 kilogram. From this we can calculate how much the mole of nitrogen and helium. So number of moles for nitrogen is mass of nitrogen divided by the molar mass of nitrogen. So mass of nitrogen 0.35 kilogram divided by the molar mass of nitrogen is 28. So we get here 0.0125 kilomole of nitrogen. This is not absolute value, this is specific per kilogram. Similarly we do for helium, so it will be 0.65 divided by molar mass for helium is 4. So we get 0.1625 kilomole. Now we can calculate the total number of moles is number of moles for nitrogen plus number of moles for helium. So the total number of moles is 0.175 kilomole. Again, this is not absolute value, this is per kilogram. As the fraction or the percentage is not affected by the amount of mass or mole, the absolute value. So if we have 1 kg or we have 10 kg, mass ratio remains the same. Similarly, the mole ratio will remain the same. The mass or mole percent or fraction is not affected by our assumption. So we can calculate the mole fraction of nitrogen is number of mole of nitrogen divided by total number of mole. And since both these values are per kilogram, so kilogram will be cancelled from both sides. As a ratio, this ratio remains true. So we can see that nitrogen has 7.14% by volume. We calculate for helium. So the rest will be helium, which is 92%, 0.8. Now we can calculate the molar mass of the mixture. So the molar mass for the mixture is the summation of the molar mass of the components multiplied by their molar fraction or volume fraction. So first we calculate for nitrogen, then we calculate for helium. So the molar mass is 5.7 kilogram per kilomole. Now we can calculate the work done. So the work is, in this case, isobaric compression. So it will be P delta V, since the pressure is constant. And since we are using ideal gases, so we can use the ideal gas equation here. So P delta V will equal R delta T. In this case, we don't know how much the gas constant for the mixture, so we use the universal gas divided by the molar mass of the mixture. We don't have to convert from degree Celsius to Kelvin. We can use directly the degree Celsius values. So the work done is 320 kilojoule per kilogram. So the second question, we have a mixture of gas and vapor, so we will need to use the steam table. We have two conditions. The initial condition is at 180 degrees Celsius and 1.2 megapascal. Then we cool down to 100 degrees Celsius. So at 180 degrees Celsius we have the dryness is 100%, or the quality of the steam X equals 1, means we don't have any condensed water. while when we drop the temperature, we'll have some water condensed in the container. So first we study at 180 degrees Celsius. So the steam is in the red color and the air is in the blue color. So mass of air is 0.2 kilogram. So the most important values that we have to look for in the steam table, we choose first the 180 degrees Celsius. We have to know the saturation pressure at this point. Also, we need to know the specific volumes for water and for gas. For 180 degree, we don't have any water, so this value is not very important, but the specific volume for gas is important. Then the second point is at 100 degrees Celsius, the saturation pressure, and both the specific volume for water and for steam are important. So we have to write them down. We are following here Dalton law. The total pressure equals the summation of partial pressure while the volume is shared. The total pressure equals air pressure plus steam pressure. So air pressure in this case will equal P total minus P steam. We can take steam pressure at 180 degrees Celsius from the steam table. So air pressure is 1200 kilopascal while steam pressure is 1002 kilopascal. So air pressure will be 197.2 kilopascal. The volume is shared between air and steam. So the tank volume at condition 1 at 180 degrees Celsius equals the volume of air, which is equal also the volume of steam, since we don't have any liquid in the tank at this temperature. So we can calculate the volume of air using the ideal gas equation. So volume of air equals mass of air multiplied by R T at first point, which is 180 degrees Celsius, but we have to convert into Kelvin, divide by the pressure. But we don't know how much the gas constant for air, so we use the universal gas constant and we divide by the molar mass for air. So we take molar mass for air in this case approximately to be 29 kilomole per kilogram. So volume of air, we calculate it will be 0.1317 meter cube, which is the volume of the vessel. And since volume of air is exactly same as volume of steam, so we can calculate now the mass of steam. So volume of air equals volume of steam, which is mass of steam multiplied by the specific volume of steam. The specific volume of steam is the same value that we take from the steam table at G, at the saturated steam. So mass of steam in this case will be 0.6795 kilogram. So the second case, we will have condensed water and we will have vapor steam as well as the same amount of air, which is 0.2 kilogram as before. However, the steam from case 1 is split into two masses, which is mass of steam and mass of water. So mass of steam at case 1 is split in this case to mass of water at case 2 and mass of steam at case 2. So this is at 180 degrees Celsius and this is at 100 degrees Celsius. So the total volume will equal in this case the volume of water plus volume of steam. Volume steam is same as volume of air, since we are following Dalton law, so the volume is shared between air and steam, while water volume is separated. So in this case, total volume will be the volume of water first, which can be represented as mass of water multiplied by specific volume of liquid. This can be taken from the steam table. So we can go back. This is the volume of fluid or liquid. So we take this value, while this one is the volume of gas. Plus the volume of steam will be mass of steam multiply by the specific volume at G point. This is all at 100 degrees Celsius. However, we already calculated how much the mass of steam in case 1 at 180 degrees Celsius is known, and the volume total we calculated at 180 degrees Celsius also known. So we can divide both and get the specific volume for case 2 at 100 degrees Celsius. As we discussed earlier, mass of steam at case 1 at 180 degrees Celsius split into two masses, mass of water plus mass of steam 2, which both at 100 degrees Celsius. So now we can calculate the specific volume for case 2. So at 100 degrees Celsius we can calculate the specific volume for both water plus steam at case 2. So this will be the total volume divided by mass of steam total at case 1, which is mass of water plus mass of steam at case 2. This will give us 0.193 kilogram per meter cube. From thermodynamics, we learned how to calculate the specific volume for gas mixture which contains water and steam. So the specific volume at case 2 will equal the specific volume of water plus X multiplied by the specific volume of mixture Fg. So this we calculated already is 0.19. So we can use the steam table to find out the specific volume of water, and the specific volume Fg is the steam minus the water, all at 100 degrees Celsius. From here we can calculate the dryness or the quality of steam, which will be 0.115. So third question, we have a diabatic gas mixture where the two tanks are insulated, there is no heat transfer and connected by a valve. So we have to calculate two cases: before opening the valve and after opening the valve, before mixing and after mixing. We need to calculate the temperature after mixing, and we need to calculate the pressure after mixing. So the temperature of the mixture and the pressure of the mixture are given in these equations. So first tank contains nitrogen in mass, the mass is given, while the second tank contains oxygen, the mole is given. So since we have this T mixture contains mass, so we have to calculate the mass of oxygen for the second tank. So the first one is to convert oxygen into the mass form. Another requirement is to calculate N, which is the total number of moles for the mixture. Lastly, we need to calculate the overall volume after opening the valve, means the volume of both tanks. So first we calculate the volume for nitrogen from ideal gas equation. So mRT divided by pressure. Since we don't know how much the gas constant for nitrogen, we use the universal gas and we divide by the molar mass for nitrogen. So in this case, the mass of nitrogen is given 2 kilogram. The universal gas constant. The temperature we have to convert from degrees Celsius into Kelvin. So volume of nitrogen is 0.322 meter cube. Before we can calculate the volume of oxygen, we have to calculate the mass of oxygen, since the value here is in mole, not in kilogram. So mass of oxygen in this case is number of moles multiplied by the molar mass of oxygen. So mass of oxygen will be 4 kilogram. Now we can calculate the volume of oxygen, since we already know the mass. So the volume of oxygen will be 2.065 meter cube. So we can calculate the total volume. So total volume will be 2.386 meter cube. For nitrogen, we don't know how much the number of moles, since the value is given in kilogram. So we calculate number of moles for nitrogen by dividing the mass dividing by the molar mass. So number of moles for nitrogen is 0.7143 kilomole. Now we can calculate the total number of moles, which is the moles of oxygen plus moles of nitrogen, which will give us 0.1964. Now we have all the data that we need, so we can calculate the temperature of the mixture after the mixing, after opening the valve. So the temperature of the mixture, we have two quantities. First, for nitrogen, the mass is 2 kg multiplied by CV multiplied by temperature in Kelvin. Then we have oxygen, 4 kg multiplied by CV multiplied by the temperature. We repeat the same in the bottom without the temperature. So the temperature is 296.4, which is 23.46 degrees Celsius. Now we calculate the pressure of the mixture. We have the number of moles multiplied by universal gas constant multiplied by the temperature of the mixture we just calculated, divided by the total volume. So the pressure is 202.88 kilopascal. Question number 4. We have also adiabatic mixing for closed system. We have a tank that is separated by a diaphragm into two rooms, into two spaces. One space contains hydrogen. The value is given by mole, while the other space contains a mixture of CO2 and nitrogen. The value is given by mass. Again, we have to use the same law to calculate how much the temperature after we remove the diaphragm and the gases are mixed. So we can solve before removing the diaphragm, then we solve after removing the diaphragm. So we can divide the tank into two spaces. One space we call it A, the second space we call it B. So the molar mass for A will equal the summation of the mole fraction multiplied by the molar mass for the components. We have here two components. We have CO2 and we have nitrogen, and we know the mole fraction for each one. So we can calculate the molar mass for space A. Mole fraction for CO2 is 0.4 multiplied by the molar mass of CO2 is 44, plus mole fraction for nitrogen is 0.6 multiplied by the molar mass for nitrogen is 28. So the molar mass of the mixture is 34.4 kilogram per kilomole. Now we can calculate the mass fraction for CO2 and for nitrogen. Since we have only the mole fraction, we can convert from mole fraction into mass fraction by multiplying by the molar mass ratio. So the law here, the mass fraction equals the mole fraction multiplied by the molar mass ratio, which is the molar mass for the individual divided by the molar mass for the mixture. So in this case, molar mass fraction for CO2 will equal 44 divided by 34.4, the mixture molar mass, multiplied by 0.4, the volume fraction. So the mass fraction is 0.5116. We can calculate directly the mass of CO2 is 51% of the total mass, which is 10 kilogram, which will give us 5.116 kilogram. Similarly, we calculate the mass fraction for nitrogen. So mass fraction for nitrogen is 0.48, which is 48%, 0.8. So we can calculate mass of nitrogen is 48% of 10 kg, which will give us 4.88 kilogram. At this point, we already can calculate after the mixture, but we will calculate two methods. One using the CV for individual CO2 and for nitrogen, and one CV calculated for the space A. So we have two ways to solve this problem. So let's calculate CV for space A. So CV for space A, since this is per kilogram, so we need to multiply by the mass fraction. So the calculation is the summation of mass fraction multiplied by CV for the individual component. So we have the mass fraction of CO2 is 0.511 multiplied by CV is giving for CO2. Then we calculate for nitrogen. In this case, CV for the space A will be 0.699 kilojoule per kilogram Kelvin. Now we calculate after mixing. We can use two methods for the calculation. Either we calculate three individual gases or we calculate two spaces, space A and space B. So let's calculate first using three individual gases. So T mixture will be three gases. First is CO2. The mass for CO2 is 5.11 multiplied by CV multiplied by temperature 27 degrees Celsius, which is 300 Kelvin. Then we have nitrogen. Lastly, we have hydrogen. For hydrogen, the mass is unknown, so we have to calculate the mass first. So mass of hydrogen in this case will be number of moles for hydrogen multiplied by the molar mass of hydrogen gas. So mass of hydrogen is 15 kilogram. The temperature is 40 degrees Celsius, which is 313 Kelvin. We repeat the same in the bottom without the temperature. So the temperature in this case is 312.4 Kelvin. Another way to solve it is using space A and space B. So we'll have only two brackets, not three brackets. So in this case, temperature of the mixture will be space A is the mixture of CO2 and nitrogen. So the mass is 10 kg. And we take the CV for space A that we just calculated multiplied by the temperature. Then we have for space B, it contains only hydrogen. So hydrogen is 15 kg multiplied by CV multiplied by temperature. In the bottom we use the same brackets but without the temperature. So we'll get the same value. Mean temperature of the mixture is 314.4 Kelvin. So last question, question number 5 is also adiabatic mixture, but for open system. The only difference here is we use enthalpy instead of internal energy. So we will use Cp instead of Cv. So we have Y-shaped mixer. For simplicity, we call this stream number 1 and this stream number 2. This will be stream 1 plus 2. So since we have adiabatic mixer, so we have the Q equals 0. Also we don't have any work, so W equals 0. So enthalpy inlet will equal enthalpy outlet. So enthalpy inlet is M1 Cp1 T1 plus M2 Cp2 T2 will equal the exit is M1 Cp1 plus M2 Cp2 all multiplied by the temperature at the exit, which is the mixture temperature. So we can calculate the mixture temperature by dividing this value on this value. So we calculate for stream 1 and stream 2. Note that we have to convert from degrees Celsius into Kelvin. At the bottom we write the same but without the temperature. So the mixture temperature in this case is 305.5 Kelvin, which is 32 degrees Celsius 0.5. Since the flow rate here is in mass, so we have to calculate the volume flow rate in kilomole per second. So the mole flow rate for stream number 1, we calculate it by dividing the mass flow rate divided by the molar mass. Similarly for stream number 2, so the volume flow for the second stream is 0.18 kilomole per second. Now we can calculate the molar fraction. So for stream 1, we have number of moles for stream 1 divided by number of moles for stream 1 plus number of moles for stream 2. So stream 1 represents about 51% of the total stream. Similarly, we calculate the molar fraction for stream number 2. So it will represent around 48%. Now we can calculate the molar mass of the mixture. So the molar mass will be 23.2. Finally, we can calculate the gas constant of the mixture by dividing the universal gas constant by the mixture molar mass that we just calculated. So the gas constant for the mixture will be 0.358 kilojoule per kilogram Kelvin. This will conclude this tutorial. Thank you for watching.